It turns out that integration in polar, cylindrical, and spherical coordinates is a subset of a larger class of integration techniques known as change of variables, or change of coordinates. A change of variables is conceptually no different from a U substitution from single variable calculus, where we replace one symbol with another because it's more convenient for some reason. The challenge is that this is actually a very complex process. We're going to start with the two-variable change of coordinates, and we're going to use polar coordinates as our model. The framework for change of variables is that we have two coordinate systems. One of those coordinate systems is the standard xy plane. On this plane, we have a region R that has some sort of complexity to it. The idea is that in a different coordinate system, we can find a region S that is simpler and easier to work with that happens to map onto R under some transformation T. Optimistically, we can even hope that we end up with a simple rectangle after the change of coordinates. In this case, we might recognize this region as a polar rectangle, and that gives us the idea that polar coordinates might be a good choice. There's nothing telling us this other than our experience, and it can be very difficult to identify a good change of variables substitution in general. Notice that on the r theta plane, the region is represented as a true rectangle. We can explicitly write down this formula using our polar coordinate substitutions. Notice that under T, the rectangle in the r theta plane gets mapped to the polar rectangle. Each side of the r theta rectangle matches up with one of the curves in the xy plane. There's a warping of the shape that changes the area, and we're going to need to figure out how to compensate for that. For polar coordinates, we explicitly worked out that the warping factor was r, and that's related to the fact that the polar rectangle gets larger when r gets larger, even if you keep dr and d theta the same. In this case, we had to explicitly work out the geometry. The goal of the next section is to work that out for a general transformation. For polar coordinates, we had to use the details of the transformation and geometric considerations in order to get the appropriate scaling factor. The general change of coordinates process is a bit more complicated because we have to work in the abstract. We're going to start with a transformation that maps from the st plane to the xy plane. We will assume that the coordinates in the xy plane are denoted by the functions x of st and y of st. Now we're going to imagine tracing a small rectangle in the st plane and take a look at what happens to it in the xy plane. We'll set the bottom left corner of the st rectangle to be the point AB and the sides of the box to be delta s and delta t. When we map this to the xy plane, the three corners get mapped to these 3 points. We can see that the shape of the region is probably not all straight sides, but because the values are small, it will be close. To approximate the area, we're going to use the parallelogram formed by 2 of the sides. We can get the expressions for these vectors by subtraction. Notice that we can factor out a delta s or delta t to make these look like difference quotients. Then we can take the limit as delta s and delta t go to 0 to get these partial derivatives and differential terms. At this point, I'm diverging from the book's presentation, but we'll see that we end up in the same place when we're done. The notation is a little bit sloppy, but I think it's much easier to understand. The partial derivative of a vector function with respect to s or t is just the vector formed by the partial derivatives of the components. So these two expressions really do make sense as vectors, and we'll see what they look like in a moment. The point right now is that we can calculate the area element dA from these by taking the length of their cross product. This gives us a concise expression for the area element that we could substitute in to calculate the integral. We are now going to see that this relates back to the book's version by writing everything out explicitly. When we said that the area of the parallelogram was the cross product, we implicitly went up to 3 dimensions, but where the z-coordinate was always 0. So as we work this out, we're going to explicitly write in that dimension to make the calculations work. We will first work out the partial derivatives, and then compute the cross product. It will turn out that the I and j components will be 0, so that taking the length of the result is straightforward. This last form is the same form that's in the book. The quantity involving the partial derivatives is known as the Jacobian, and is denoted with this shorthand notation. This is actually just the determinant of this 2x2 matrix, where the pattern is that the rows all have the same dependent variable, and the columns have the same independent variable. This gives us another way to write down the area element. And now that we have the area element, we can write down the formula for the change of coordinate calculation. To do a calculation of this type, you're often going to have to come up with a substitution yourself. The problems usually give you a big hint by looking at the form of the integrand or the boundary. Usually they will imply substitutions by how terms are grouped together. For example, in activity 11.9.4, you are trying to calculate this integral. Notice how the integrand strongly suggests a substitution for x plus y and x minus y. If the problems did not point you in the right direction, you likely would not be able to do the calculation. This idea can be generalized to more variables by using a higher dimensional Jacobian. The general process is still the same, but now you have the determinant of a 3x3 matrix as your scaling factor. This is what the Jacobian looks like. We're not going to show the derivation of this because it's just too much at this stage. But if you followed along with the derivation from the previous section, you can probably come to a good understanding of how this works. For this class, you are merely expected to be able to follow the process. For example, you can verify our formulas for dv in both cylindrical and spherical coordinates by using the substitutions we developed in the previous section and just working out the details. Doing problems is a bit of a process as there are a bunch of steps, including making sure that you've got the right transformed region. But I think the book does a pretty good job of holding your hand through it. Because while the calculations themselves are not any more difficult than the problems in previous sections, the entire setup can be a bit rough. There's a reason that this is the last section of the book. But if you've been doing the exercises over the last 3 chapters, there's nothing here that you shouldn't be able to do. And that's it for this course. I hope you've enjoyed the videos and you've learned a few things about multivariable calculus. Thanks for watching.